Before the internet connected America with invisible signals, another network already tied the nation together, one wire at a time. It wasn't made of apps, satellites, or smartphones. It was made of copper, switchboards, telephone poles, and an army of operators, engineers, and linemen. It was called the Bell System, and for generations, it was the closest thing America had to a national nervous system. This was the machine that let voices travel farther than ever before. It turned communication from something slow, delayed, and written into something immediate, human, and alive. Before Bell, messages moved at the speed of paper and telegraph code. After Bell, a voice could cross a city, then a state, then an entire continent. But this isn't just the story of the telephone. It's the story of how America learned to speak in real time, and how one company built, controlled, and eventually lost the most powerful communication network the country had ever seen. Before Google, before Wi-Fi, before the web, there was Bell. And in many ways, the modern world began with that first call. Chapter 1. A Nation That Could Not Speak. During the middle of the 19th century, the United States stretched across a continent, but functioned like a collection of distant islands. Messages traveled slowly. Voices did not travel at all. A merchant in Chicago who needed to confirm a shipment from New York faced delays measured in days. A railroad superintendent trying to coordinate trains across several states relied on handwritten orders carried by telegraph offices. Families separated by migration waited weeks for letters. Communication existed, but it moved at the speed of paper, rail, and human relay. The fastest system available was the telegraph. Telegraph wires began spreading across the country in the 1840s and 1850s. Thin iron lines followed railroad tracks and crossed open plains. Wooden poles marched across farmland and towns. Inside telegraph offices, operators tapped metal keys that sent electrical pulses along the wires. Those pulses carried coded messages. Not speech, not sound, only patterns. Morse code turned language into dots and dashes. An experienced operator could send perhaps 40 words per minute. Another operator at the receiving station translated the pulses back into text. The message was then written down and delivered by hand. It was faster than the postal system, but it was not conversation. A telegraph exchange functioned more like a relay station than a communication network. Messages often passed through several intermediate offices before reaching their destination. Each relay introduced delay. Each operator added the possibility of error. By the 1860s, the largest telegraph network belonged to Western Union. Their wires stretched tens of thousands of miles across the United States. Messages connected New York banks with Chicago grain markets and San Francisco shipping agents. But even this vast system could not carry a human voice. The limitation was technical and fundamental. Telegraph equipment was designed to send simple electrical pulses. The current switched on and off in sharp bursts. Speech, however, required something entirely different. Human voices produce complex vibrations in air. Those vibrations change continuously. To reproduce speech at a distant location, an electrical signal would have to copy every subtle variation of those sound waves. No existing telegraph system could do that. Scientists and engineers understood the problem well enough to recognize how difficult it was. A machine capable of transmitting speech would require a device sensitive enough to convert sound vibrations into electrical fluctuations, then reproduce those fluctuations through another device at the receiving end. The technology simply did not exist. Many inventors tried anyway. Throughout the 1860s and early 70s, researchers in Europe and the United States experimented with what they called harmonic telegraphs. These devices attempted to send multiple signals along a single wire using different frequencies. The goal was efficiency. Telegraph companies wanted to increase the number of messages each wire could carry. Few of these experiments worked reliably. The wires themselves created obstacles. Electrical signals weakened as they traveled longer distances. Interference from weather and nearby lines distorted transmissions. Even small changes in resistance along the wire could alter a signal. Telegraph engineers fought these problems constantly. Storms snapped poles. Ice accumulated on lines until they sagged or collapsed. Lightning strikes destroyed equipment in small wooden offices scattered across rural towns. Linemen climbed poles in freezing winds to splice broken wires and restore service. Yet despite all the effort, the telegraph remained limited to coded pulses. Communication through telegraph also required trained specialists. Ordinary citizens rarely touched the equipment. A person entered a telegraph office, wrote a message on paper, and paid a fee based on word count. The operator translated the message into Morse code and sent it along the network. At the receiving end, another operator decoded the pulses and wrote the message down again. Every message passed through human hands. This structure created bottlenecks in busy cities. Telegraph offices in places like New York sometimes handled thousands of messages in a single day. Operators worked long shifts at cramped desks surrounded by clicking instruments. Accuracy depended on skill and concentration. A tired operator could easily misread a sequence of pulses. One misplaced dot could change the meaning of an entire sentence. For businesses that relied on rapid information, even small mistakes could cost money. Railroads depended heavily on telegraph communication. Dispatchers used coded messages to coordinate train movements across hundreds of miles of track. Without telegraph instructions, trains risked meeting head-on along single-track routes. Telegraphy improved safety compared with earlier methods, but it still required constant supervision and careful timing. The limitations became obvious whenever people tried to communicate something urgent. Imagine two businessmen negotiating a shipment price. With telegraph messages, each exchange required writing, sending, decoding, and delivering. Even under ideal conditions, the process took time. Questions and answers moved slowly back and forth. A spoken conversation could solve the same negotiation in minutes. Yet no machine allowed that. Inventors occasionally proposed mechanical speaking tubes or acoustic systems, but these worked only across short distances inside buildings. A person might shout through pipes between factory floors. The sound faded quickly beyond a few hundred feet. Electrical transmission of speech remained theoretical. By the early 1870s, the United States had already built a massive communication infrastructure. Tens of thousands of telegraph poles crossed the landscape. Telegraph companies operated hundreds of offices in towns large and small. The wires existed. What they lacked was a device capable of turning speech into electricity. Several inventors believed such a machine might be possible. Among them was a young teacher of the deaf named Alexander Graham Bell. Bell's interest in sound began long before the idea of a telephone network appeared. His family studied speech and hearing. His father developed systems for teaching pronunciation to deaf students. Bell himself spent years experimenting with ways to represent sound visually and mechanically. These experiments focused on the physics of vibration. Bell believed that sound waves could be reproduced through electrical variations if the right mechanism existed. Instead of sending simple pulses like a telegraph key, a device would need to produce a continuously changing current that matched the pattern of speech. The concept seemed radical. Telegraph engineers viewed communication as an on or off system. A signal either existed or it did not. Bell imagined something entirely different, an electrical current that fluctuated constantly, rising and falling in perfect rhythm with a human voice. If such a signal could travel along a wire, then speech itself might travel with it, in theory. The challenge was building the apparatus. Bell and several other inventors began constructing experimental devices that used diaphragms and magnets to convert sound vibrations into electrical movement. Early prototypes produced faint noises rather than clear speech, but they demonstrated something important. Electricity could carry more than simple pulses. Within a few years, one of those experimental devices would send the first recognizable spoken words across a wire. That moment would change the purpose of communication networks across the United States. The telegraph wires that already crossed the continent would soon carry something far more powerful than coded messages. They would carry voices. Chapter 2: Alexander Graham Bell's Impossible Machine. In the early 1870s, the idea of sending human speech through a wire sounded unrealistic to most engineers. Telegraph companies had spent decades refining systems that transmitted simple electrical pulses. Those signals carried coded messages across great distances, but they could not carry a voice. Alexander Graham Bell believed that limitation might be temporary. Bell did not begin his career as an electrical engineer. His background came from the study of sound and speech. His father, Alexander Melville Bell, created a teaching system called visible speech. The method used written symbols that showed how the tongue, lips, and throat produced specific sounds. The system helped deaf students learn pronunciation. Growing up in that environment, Bell developed a deep curiosity about how sound worked. Speech was not only language, it was movement in the air. Pressure waves changed shape constantly as words formed. Bell became fascinated by the possibility of copying those patterns using electricity. After moving to the United States, he began teaching at schools for the deaf in Boston. During the day, he worked with students. At night, he conducted experiments in small, rented workshops filled with magnets, wires, and thin metal diaphragms. The problem he was trying to solve began with the telegraph. Telegraph companies wanted to send several messages along a single wire at the same time. This idea was known as the harmonic telegraph. Each message would use a different electrical frequency, allowing multiple signals to travel together without interference. Bell began experimenting with that concept. His early devices used metal reeds tuned to specific tones. Each reed responded only to its own frequency. The system showed promise, and two Boston businessmen soon agreed to support his research. Their names were Gardner Green Hubbard and Thomas Sanders. But Bell's experiments slowly moved in another direction. While studying vibrating metal reeds, he noticed something important. Sound waves changed continuously. Telegraph signals did not. They switched on and off like a simple electrical gate. If electrical current could vary smoothly instead of switching sharply, the current might carry the shape of a sound wave. That idea became the foundation of the telephone. To test the theory, Bell built an experimental transmitter using a thin diaphragm placed near a magnet wrapped in wire. When someone spoke toward the diaphragm, sound waves caused the metal surface to move slightly. That movement disturbed the magnetic field and produced small changes in electrical current. At the receiving end, another diaphragm connected to a magnet responded to those fluctuations. If the electrical variations matched the original sound wave, the second diaphragm would move in the same pattern. The air near that diaphragm would shift. Sound would emerge. The first attempts produced only buzzing noises. The signal was weak. The equipment lacked sensitivity. Clear speech remained out of reach. Bell continued modifying the apparatus. By early 1876, he and his assistant Thomas Watson were building experimental transmitters and receivers in a modest laboratory in Boston. The equipment looked improvised. Wires crossed wooden tables. Batteries powered magnets mounted inside rough frames. Yet the basic principle was beginning to work. At the same time, another inventor was approaching a similar breakthrough. Elisha Gray, an engineer from Illinois, had developed a design that used a liquid transmitter to convert sound waves into electrical changes. Both men were exploring ways to send speech through wires. Their work would soon collide at the United States Patent Office. On March 7, 1876, Alexander Graham Bell received a patent describing a method for transmitting vocal sounds electrically. The document would later become one of the most valuable patents in American industrial history. Only a few days later, Bell and Watson achieved the result they had been pursuing. On March 10, 1876, Bell accidentally spilled acid from a battery used in their experiment. He called out to Watson, who was working in another room connected by wire.
Watson, come here. I want to see you.
Watson heard the words through the receiver.
What did I say?
They were faint
Watson,
but
come here. I want to see you.
unmistakable. For the first time, a human voice had traveled along an electrical wire and reappeared as sound in another room.
Mr. Bell,
The principle had
do
been
you
proven.
understand?
Bell
what
and
I said?
Watson immediately began refining the design. Early transmitters generated extremely weak signals. Voices could travel only short distances before fading. Despite the limitations, demonstrations of the new device began attracting attention. In June 1876, Bell presented the telephone at the Centennial Exhibition in Philadelphia. The exhibition celebrated 100 years since the signing of the Declaration of Independence. Inventors from many countries displayed machines and industrial equipment. Bell's small instrument looked unimpressive beside massive steam engines. But when visitors listened through the receiver, they heard something extraordinary: a voice speaking through a wire. Among the observers was Emperor Dom Pedro II of Brazil. After hearing the demonstration, he reportedly reacted with surprise and excitement. News of the invention spread quickly among scientists and investors. Many telegraph engineers remained skeptical. Telegraph networks already handled enormous volumes of information. The telephone appeared fragile. Its signals weakened quickly over long distances. Yet Bell believed the invention had a different purpose: conversation. Instead of sending formal written messages, people could speak directly to each other. Business negotiations could happen instantly. Doctors could deliver instructions without traveling. Families could communicate across cities in real time. Communication would change from delayed exchange to immediate interaction. Bell's financial backers soon recognized the opportunity. In 1877, they created the Bell Telephone Company. At first, the business installed telephones in pairs, linking offices or homes with direct wires. But as the number of subscribers increased, that approach quickly became impractical. The system needed a central location where calls could be connected between many users. Operators would plug wires into switchboards to create temporary circuits between telephones. The first telephone exchanges would soon appear. The fragile experimental machine built in Bell's Boston workshop had solved the most important obstacle. Human speech could travel through electricity. Once that barrier disappeared, engineers could begin tackling a much larger challenge: building a network that allowed an entire nation to speak. Chapter 3: The Birth of a Network. When the first telephones appeared in American cities during the late 1870s, they worked in the simplest possible way. Two instruments were connected by a single wire. Lift the receiver and speak. The voice traveled directly to the other telephone. That design worked for two people.
Hello?
It failed as soon as a third
how's it
person
going?
joined.
Good, how are you?
Imagine a city with 100 telephones. If each subscriber wanted to speak with every other subscriber, the number of required wires exploded. Thousands of lines would have to run across streets, rooftops, and poles. The cost alone would make the system impossible. Engineers quickly realized the telephone needed something the telegraph had used for years: a central switching point. Instead of connecting every pair of telephones with separate wires, each line could run to a central office. From that location, operators could temporarily link two subscribers together. When the conversation ended, the connection disappeared. The idea created a communication grid. One of the first commercial telephone exchanges opened in New Haven, Connecticut on January 28, 1878. The small system served only 21 subscribers. Most were businesses that needed faster communication within the city. Each subscriber line ran directly to the central office. Inside the building stood a wooden switchboard mounted along the wall. Dozens of wires terminated in metal sockets. When a user lifted the receiver and signaled the office, an operator answered the call. The operator asked a simple question: "Number, please?" The caller named the subscriber they wanted to reach. The operator inserted a cord with metal plugs into two sockets on the board. One plug connected the caller, the other connected the receiving line. Electric current flowed between the wires. A temporary circuit formed. The conversation began. When the call ended, the operator removed the plugs. The lines returned to standby, ready for the next connection. The system looked simple. In reality, it demanded constant attention. Each central office handled dozens of calls every hour. Small signal shutters dropped open when a subscriber requested a connection. Bells rang softly across the switchboard room. Operators had to respond instantly. Speed mattered. If several calls arrived at the same moment, operators connected them one after another while remembering which lines were waiting. A mistake could link the wrong subscribers together. Conversations might cross. Customers complained quickly when errors occurred. The earliest operators were often young boys. Telephone companies soon discovered that arrangement created problems. Many boys treated the work casually. They joked with callers, argued across the lines, or left their stations during busy periods. Managers began searching for a more disciplined workforce. They found it in young women. In 1878, a woman named Emma Nutt became the first female telephone operator in Boston. Her calm voice and careful manner impressed company managers. Soon, telephone companies began hiring women in large numbers. By the 1880s, female operators dominated the profession. Training became formalized. Operators learned to recognize signal indicators, manage cords efficiently, and memorize subscriber numbers across the city. Some switchboards required operators to remember hundreds of connections. Large boards resembled walls covered with rows of small openings. Each opening represented a subscriber line. Below them hung pairs of cords ending in metal plugs. The operator worked constantly with both hands. One hand answered signals, the other connected circuits. Eyes scanned the board for new requests. Ears listened for instructions through headsets. A skilled operator could connect hundreds of calls during a single shift. As the number of subscribers increased, central offices expanded rapidly. Buildings in large cities filled entire floors with switchboard equipment. Rows of operators sat shoulder to shoulder, each responsible for a section of the board. Behind the switchboards ran bundles of copper cable entering from the streets. Telephone lines spread quickly across urban poles. Photographs from the 1880s show streets filled with overhead wires. Thousands of lines stretched between buildings and wooden poles. The system worked, but it looked chaotic. Engineers gradually began routing many lines underground through protective conduits. Underground cables reduced storm damage and improved reliability in dense cities. Even with those improvements, maintaining the growing telephone system required constant labor. Linemen climbed poles daily to repair damaged lines. Storms snapped wires. Construction crews cut cables. Equipment inside central offices wore out from continuous use. Technicians and repair crews kept the system operating. Despite these challenges, the number of subscribers increased steadily. Businesses adopted telephones first. Banks, shipping firms, factories, and newspaper offices all benefited from instant communication. Orders could be placed immediately. Prices could be negotiated without delay. Doctors soon installed telephones in their offices and homes. Patients could request medical help without traveling across the city. Hospitals used the system to coordinate urgent treatment. Gradually, the telephone entered private homes. Early instruments remained expensive, so wealthier households adopted the technology first. But the advantage was clear. A single device connected a home to dozens of other people in the same city. For the first time, ordinary conversation moved through a technical network. Voices traveled along copper wires, through switchboards, and into distant rooms within seconds. Most calls remained local. Long-distance connections still faced serious technical barriers. Electrical signals weakened over long wires, and early transmitters produced limited power. But the basic architecture had appeared. Subscribers connected to a local exchange. Exchanges connected to other exchanges. Operators linked the entire system through manual switching. The pattern soon spread from city to city. Bell Telephone Company and its affiliates began building exchanges across the United States. Each new office extended the reach of the expanding system. What began as a few urban networks slowly developed into a national communications grid. The telephone had moved beyond invention. It had become infrastructure. Thousands of operators, technicians, and linemen now worked behind the scenes to keep voices flowing through copper wires. Their labor supported a system that grew larger every year. Soon, engineers would attempt something far more ambitious, connecting those city networks across an entire continent. Chapter 4: The Human Switchboard. Inside every early telephone network stood a room that never truly became quiet. Rows of wooden switchboards lined the walls. Thousands of wires disappeared into panels filled with small circular sockets. Lamps flickered, signal shutters dropped open. Bells rang softly in the background. At long desks in front of those boards sat the people who made the system function: telephone operators. During the early years of the Bell network, these workers formed the living control system of the entire telephone infrastructure. Every call passed through their hands. Without them, the network would simply stop. A subscriber lifted the receiver. The local exchange detected the signal. On the switchboard, a small indicator dropped open or a lamp appeared beside the subscriber line. The operator answered immediately. "Number, please." The caller named the destination. The operator reached for a cord hanging below the board. One plug connected the caller's line. A second plug connected the destination line. Electric current flowed between the wires. A temporary circuit formed. The conversation began. When the call ended, the operator removed the plugs. The lines returned to standby, ready for the next request. The process seemed simple. In reality, it demanded constant attention. Each exchange handled dozens of calls every hour. Indicators opened across the board without warning. Operators had to notice each signal immediately while remembering which subscribers were already waiting. One mistake could disrupt several calls. If the wrong lines connected, two strangers might suddenly hear each other speaking. If a cord remained plugged too long, the line stayed occupied and blocked new calls. Customers complained quickly when connections failed. Accuracy mattered as much as speed. Telephone companies soon realized the job required patience, discipline, and strong memory. Operators needed to recognize subscriber numbers, street locations, and sometimes the voices of frequent callers. The earliest exchanges experimented with several types of workers. Young boys often filled the role during the first years of service. The results proved disappointing. Many boys treated the work casually. They joked with callers, argued across the lines, and occasionally abandoned the switchboard during busy periods. Managers began searching for a more reliable workforce. In September 1878, a woman named Emma Nutt took a seat at a Boston telephone exchange. Her calm voice and careful manner impressed supervisors immediately. Customers noticed the difference as well. The change spread quickly. Within a few years, telephone companies across the United States began hiring women almost exclusively for operator positions. By the 1880s, the switchboard workforce was overwhelmingly female. Most operators were young and unmarried. Telephone companies believed younger workers learned the system quickly and spoke with clearer voices. The hiring process could be strict. Applicants needed clear speech, good hearing, and polite manners. Some companies tested candidates by asking them to repeat long sequences of numbers or respond to rapid instructions. Training followed. New operators learned the geography of their city along with the layout of the switchboard. They practiced connecting calls quickly while supervisors watched their movements. Speed improved with repetition. Accuracy came from discipline. Once fully trained, an operator took her place along the board for long shifts. The design of the switchboard shaped the rhythm of the job. Each operator managed a section of subscriber lines. Hundreds of small openings covered the panel. Below them hung pairs of cords ending in metal plugs. The operator worked constantly with both hands. One hand answered signals, the other connected circuits. Eyes moved across the board, searching for new requests. Ears listened through a headset receiver. A busy exchange rarely paused. During peak hours, operators connected calls one after another without interruption. Experienced workers learned to anticipate requests from regular customers. A business office might call the same supplier every morning. A newspaper editor might contact reporters across town throughout the afternoon. Operators remembered patterns. Despite the technical setting, the work demanded emotional control as well. Operators sometimes heard fragments of private conversations while connecting calls. Company rules required strict neutrality. They were never supposed to comment, react, or interfere. Telephone companies enforced discipline through detailed regulations. Operators had to maintain a steady tone of voice. Arguing with callers was forbidden. Eating at the switchboard was prohibited. Talking with nearby operators during work could result in reprimands. Supervisors walked quietly through the room, watching for mistakes. Long shifts made the job physically demanding. Operators sat upright for hours while reaching repeatedly for cords above shoulder height. The motion repeated thousands of times each day. Some workers developed strained arms and stiff necks from the constant movement. Noise filled the room as well. Bells rang. Switchboard shutters snapped open. Voices passed through hundreds of circuits at the same time. Yet the work continued without pause. Despite the strain, the job offered stable employment for many women. Telephone companies paid modest wages, but the work provided income and independence that few other professions offered at the time. By the early 20th century, thousands of operators worked across the expanding Bell network. Large city exchanges employed entire floors of workers. Photographs from the period show long rows of operators seated side by side beneath towering switchboards, while supervisors monitored the signals. Behind those rooms stretched the physical infrastructure of the telephone network. Bundles of copper wires entered the building through underground conduits or overhead lines. Those wires connected homes, businesses, hospitals, and government offices across the city. Every call began and ended at the switchboard. The operators formed the bridge between those wires. Their hands built the temporary electrical pads that allowed voices to travel from one place to another. Each connection lasted only minutes before the cord separated and the circuit disappeared. Then another signal arrived. As the number of subscribers increased, the manual switching system faced growing pressure. Large cities processed tens of thousands of calls each day. Even the most skilled operators struggled to keep pace. Engineers began searching for a new solution. Machines, they believed, might eventually replace the human switchboard. But during the early decades of the telephone network, no machine could match the flexibility and judgment of a trained operator. For millions of Americans, the first voice they heard when using a telephone was not the person they were calling. It was the operator who connected the call. Chapter 5: Stringing Copper Across a Continent. By the early 1880s, the telephone had proven its usefulness inside cities. Local exchanges connected businesses, doctors, and households through networks of switchboards and copper wires. Within a single town, voices traveled clearly from one building to another. Beyond the city limits, the technology faced a much larger obstacle: distance. A telephone signal weakened as it moved along a wire. Electrical resistance inside the copper slowly reduced the strength of the current. After enough distance, the voice arriving at the far end became faint and distorted. Within a few miles, the effect was manageable. Across hundreds of miles, it became severe. Early telephone transmitters produced only small electrical variations. As wires stretched farther, voices became fainter. Conversations that sounded clear inside a city exchange often became difficult to understand across rural lines. Engineers faced an urgent question. If the telephone was going to connect an entire nation, how could the signal survive the journey? The first step involved building the physical routes. Telephone companies began extending pole lines beyond urban areas. Wooden poles marched across farmland and along railroad corridors. Each pole carried horizontal crossarms supporting several parallel wires. Glass or ceramic insulators separated the wires from the wood. Without those insulators, electrical current would leak into the pole and weaken the signal even further. Linemen built much of this infrastructure by hand. Crews transported poles by wagon or rail. Each pole had to be lifted upright and buried deep in the ground. Once the line of poles stood in place, workers climbed them using metal spikes strapped to their boots. From those heights, they stretched copper wire from pole to pole, tightening the line until it hung with the correct tension. The work demanded balance and strength. A lineman stood high above the ground while guiding heavy wire through wind or rain. One slip could lead to a fall. Storms sometimes destroyed entire sections of pole line, forcing crews to rebuild miles of infrastructure. Despite the danger, the telephone network continued expanding. By the late 1880s, long-distance routes began linking major American cities. Businesses could now hold conversations between places that once relied entirely on telegraph messages. But the signal problem remained. Engineers studying transmission lines discovered that telephone wires behaved as complex electrical systems. Long wires possessed both inductance and capacitance. These properties changed the way speech signals traveled along the line. Without correction, higher sound frequencies faded quickly. Words became muffled. During the 1890s, researchers began exploring ways to improve the transmission. One of the most important breakthroughs involved the loading coil. An engineer named George Campbell, working for American Telephone and Telegraph, developed a practical method for improving signal transmission. His design added small inductive coils at regular intervals along a telephone line. These coils altered the electrical characteristics of the wire. Speech signals could travel farther before weakening. Around the same time, another engineer named Michael Pupin developed a similar concept and later patented the approach. The Bell system soon adopted loading coils throughout its expanding network. Technicians installed the devices along long-distance routes, often roughly every mile. Each loading coil consisted of copper wire wound around a magnetic core and sealed inside a protective case. The equipment could be mounted on poles or housed in underground enclosures. The improvement was dramatic. Voices that once faded after a few dozen miles could now travel much farther while remaining clear enough for conversation. With the signal problem partially solved, construction accelerated. Telephone companies began building stronger long-distance routes, linking major cities across the eastern United States. Heavy copper conductors replaced earlier wires. Improved insulators protected the circuits from weather. Engineers paid careful attention to the mechanical behavior of the lines. Copper wire expanded in summer heat and contracted during winter cold. If tension became too tight, the wire could snap. If it became too loose, the line sagged dangerously low. Spacing between poles had to be calculated carefully so the wire remained stable throughout changing seasons. Railroad corridors often provided ideal routes. Railroads already crossed large portions of the country. Their right-of-way offered clear paths for pole lines stretching across long distances. Telephone companies installed wires alongside the tracks, allowing maintenance crews to reach remote sections more easily. Even with improved engineering, building long-distance telephone lines remained expensive. Each mile required poles, wire, insulators, and skilled labor. Crews surveyed routes, transported materials, and maintained the infrastructure after installation. Storm damage, lightning strikes, and falling trees frequently interrupted service. Yet demand for long-distance communication continued growing. Businesses wanted immediate contact with suppliers and markets in distant cities. Banks needed rapid information about financial conditions across the country. Newspapers sought faster communication with reporters and correspondents. The telephone offered something the telegraph never provided: direct conversation. Two people separated by hundreds of miles could speak to each other instantly. Questions received immediate answers. Negotiations unfolded naturally instead of through written messages. The economic value was enormous. As the network expanded, American Telephone and Telegraph gradually assumed responsibility for long-distance service. Local Bell companies continued operating city exchanges, while AT&T concentrated on building the trunk lines that connected those exchanges together. These trunk routes formed the backbone of the national telephone system. Large bundles of copper wire stretched between major cities. Each pair of wires carried a single conversation. Switchboards in long-distance offices connected calls from local exchanges onto these trunk circuits. Operators coordinated the connections. When a subscriber requested a long-distance call, the local operator contacted another operator in the distant city. Several switching offices sometimes worked together to complete the route. The process could take several minutes. But once connected, the voices traveled instantly. By the early 20th century, the United States possessed a rapidly expanding web of long-distance telephone routes. The system still fell short of spanning the entire continent, but the engineering foundation had been established. Copper wires now crossed farms, forests, rivers, and mountain passes. Pole lines stretched across landscapes that earlier generations had struggled simply to traverse. The telephone network was beginning to resemble something new. Not just a collection of city exchanges, a national infrastructure. Soon, engineers would attempt their most ambitious project yet: connecting the Atlantic coast to the Pacific with a single telephone line. Chapter 6: The Coast-to-Coast Breakthrough. By the early 20th century, the American telephone network already covered enormous distances. Cities throughout the eastern and central United States were linked by long-distance trunk lines. Businesses spoke with partners in distant states. Railroads coordinated operations across large regions. Yet, one challenge remained unfinished: the continent itself. Between the Atlantic and Pacific lay mountains, deserts, forests, and thousands of miles of open land. Telegraph wires had crossed that distance decades earlier. The telephone network had not. Telephone signals weakened as they traveled along wire. Resistance, capacitance, and inductance slowly reduced the strength of the voice. Across extremely long circuits, the words arrived faint and distorted. Engineers needed a way to restore the signal along the route. The solution came from a new electronic device: the vacuum tube amplifier. An inventor named Lee DeForest had developed a component called the Audion tube. The device could strengthen weak electrical signals passing through a vacuum tube circuit. Engineers at American Telephone and Telegraph quickly recognized its importance. For the first time, telephone signals could be amplified instead of slowly fading away. AT&T engineers refined the technology and installed amplifier stations along long-distance routes. Inside small equipment buildings, vacuum tubes boosted the electrical current carrying the voice. The strengthened signal continued to the next section of line. With this breakthrough, the Bell system could attempt something previously impossible: a transcontinental telephone connection. Construction accelerated during the early 1910s. Crews pushed long-distance routes westward across the Rocky Mountains and into the deserts of the American West. Pole lines climbed steep slopes and crossed remote valleys. Building the route required enormous labor. Linemen set thousands of wooden poles across rough terrain. Copper wire stretched mile after mile along railroad corridors and mountain passes. Loading coils and repeater stations supported the circuits. The environment presented constant obstacles. Mountain winds placed heavy stress on the wires. Temperature differences caused copper to expand during summer heat and contract during winter cold. Lightning storms threatened sensitive equipment along the line. Engineers adapted each section of the route to the landscape. Amplifier stations appeared at regular intervals. Each one restored the electrical strength before sending the voice onward through the next stretch of copper wire. By 1915, the system was ready. On January 25th of that year, American Telephone and Telegraph organized a public demonstration to celebrate the opening of transcontinental telephone service. The ceremony connected New York City with San Francisco. Alexander Graham Bell participated in the event. Nearly 40 years earlier, Bell had spoken the first recognizable telephone sentence to his assistant, Thomas Watson. Now Bell prepared to repeat those same words across the entire continent. Bell stood in New York. Watson waited in San Francisco. Between them stretched more than 3,000 miles of copper wire, supported by loading coils and amplifier stations. Operators and engineers monitored the connection carefully. Bell lifted the receiver. "Mr. Watson, come here. I want to see you." Watson answered from the opposite side of the continent. "It will take me 5 days to get there now." The exchange drew laughter from the audience. The line had carried a human voice from coast to coast. What once required days of travel now happened instantly. For the first time in history, two people separated by the entire width of North America could hold a conversation in real time. The demonstration marked a turning point for the Bell system. Transcontinental calls remained rare at first. The equipment required complex coordination. Operators in several cities helped route the connection. The cost of a coast-to-coast call was high. But the engineering barrier had been broken. The telephone network could now span the continent. The achievement also revealed the scale of the national infrastructure behind the call. A single conversation traveled through multiple switching offices. Operators routed the call between trunk circuits. Amplifier stations restored the signal again and again as it crossed the country. Thousands of miles of copper formed the physical path. Each link in the chain had to function correctly. If one section failed, the entire call collapsed. Yet when every component worked together, voices moved across the continent in seconds. The accomplishment carried enormous economic implications. A banker in New York could speak directly with partners in California. News traveled instantly between the coasts. Government officials coordinated decisions across distant regions without waiting for written messages. The telephone network was beginning to operate as a national communications system. For American Telephone and Telegraph, The achievement also strengthened the company's position at the center of that system. The Bell organization controlled the equipment, the long-distance routes, and the technology required to maintain the network. Few competitors could match that scale. During the years that followed, engineers continued improving long-distance transmission. Amplifiers became more reliable. Additional trunk routes increased capacity. More cities joined the expanding system. The wires that crossed the continent carried more voices every year. The ceremony of 1915 proved that the network could span the United States, but it also revealed a new reality. A single organization now controlled the most important communication system in the country. The Bell system was becoming something larger than a telephone company. It was becoming a national monopoly. Chapter 7: The Telephone Monopoly. By the time the transcontinental telephone line opened in 1915, the Bell organization had already become the dominant force in American telecommunications. Telephone exchanges operated in cities and towns across the country. Long-distance trunk routes linked those exchanges through an expanding national grid. Behind that infrastructure stood one corporation: American Telephone and Telegraph. AT&T did not simply operate telephone lines. It controlled nearly every layer of the technology that allowed the system to function. Local service came from regional Bell operating companies. Long-distance routes belonged to AT&T itself. Telephone equipment came from a manufacturing division called Western Electric. Research and engineering flowed from another organization, Bell Telephone Laboratories. Together, these institutions formed what became known as the Bell System. The structure allowed the company to maintain tight control over the expanding network. From the beginning, Bell leaders believed the telephone network worked best as a unified system. Unlike the telegraph industry, where many companies competed along the same routes, telephone networks required coordination between thousands of wires, switchboards, and operators. A fragmented network created confusion. If several competing systems operated in the same city, each company built its own poles and wires. Subscribers connected to one network could not easily reach customers on another. Businesses sometimes installed multiple telephones on the same desk, each instrument connected to a different network. Communication became complicated. Bell executives argued that a single national system offered greater efficiency. One network, one technical standard, one organization responsible for maintaining the infrastructure. But this vision also created resistance. Independent telephone companies began appearing during the 1890s. Entrepreneurs built exchanges in small towns and rural regions where Bell had not yet expanded. Others constructed competing networks inside larger cities. Competition spread quickly. By the early 20th century, thousands of independent telephone systems operated across the United States. Some communities supported 2 or even 3 separate networks. Customers often found the situation confusing. A call from one network could not always reach another. Businesses sometimes kept several telephones so they could speak with customers connected to different systems. Bell leaders responded aggressively. American Telephone and Telegraph began purchasing smaller companies whenever possible. Independent exchanges that struggled financially often accepted buyout offers. Others faced competition from Bell's larger infrastructure and technical resources. Gradually, the Bell system absorbed many of its rivals. Control over manufacturing strengthened the company's position. Western Electric produced most of the hardware used in the Bell network. Telephones, switchboards, cables, and transmission equipment came from its factories. Engineers maintained strict technical standards to ensure every component worked smoothly within the system. Subscribers did not usually purchase their telephones. They leased them from the company. This policy prevented customers from attaching unauthorized devices to the network. It also guaranteed that Western Electric remained the primary supplier of equipment. By controlling both manufacturing and service, the Bell system maintained uniform technology across the entire infrastructure. At the center of the organization stood AT&T. The company managed the long-distance routes linking cities across the country. These trunk lines formed the backbone of the national telephone grid. Local Bell companies connected subscribers to nearby exchanges. AT&T connected those exchanges together. A call from a small town could travel through several layers of infrastructure. First, a local exchange. then a long-distance switching office, then another regional network hundreds of miles away. Every part of the route belonged to the same organization. Supporters argued that this arrangement created reliability. Engineers maintained consistent technical standards across the network. Equipment from Western Electric matched switching technology developed by Bell Laboratories. Operators followed similar procedures and exchanges across the country. The network functioned as a coordinated machine. Critics saw something different. They saw monopoly power. Independent companies complained that Bell used its scale to dominate the industry. Smaller networks struggled to interconnect with Bell lines. Customers connected to Bell exchanges could not always reach independent subscribers. Government officials began paying attention. By the early 20th century, the telephone had become essential to commerce, journalism, banking, and transportation. A communication system this important could not remain entirely outside public oversight. Regulators began examining the influence of AT&T. The company defended its position by arguing that the telephone network represented what economists called a natural monopoly. The infrastructure required enormous investment in wires, poles, switching equipment, and engineering research. Duplicating that system across competing networks wasted resources. Better, Bell executives argued, to allow a single nationwide system operating under government supervision. This idea eventually shaped American telecommunications policy. In 1913, AT&T reached an agreement with the United States government known as the Kingsbury Commitment. Under this agreement, the company promised to allow connections between Bell lines and independent telephone systems. AT&T also agreed to sell Western Electric equipment to independent companies and limit future acquisitions without government approval. In return, federal authorities allowed the Bell system to continue operating most of the national network. The agreement created a new relationship between the company and the government. The Bell system would function as a regulated utility. Government agencies would supervise rates and service standards. In exchange, the company maintained control over the infrastructure carrying most American telephone traffic. For several decades, the arrangement remained stable. The Bell system expanded its network across cities, suburbs, and rural communities. Millions of Americans gained access to telephone service. Engineers continued improving switching equipment and transmission technology. Western Electric factories produced vast quantities of equipment to support the expanding system. To customers, the network appeared simple. Lift the receiver, ask the operator for a connection, speak with someone miles away. Behind that simplicity stood one of the most complex industrial organizations in the country. A company that controlled wires, manufacturing, research laboratories, and long-distance infrastructure across an entire continent. The Bell system had become more than a telephone network. It had become the central communication system of the United States. Chapter 8. Machines that switched millions of calls. By the early 20th century, the telephone network had grown far beyond the scale imagined during its early years. Cities contained thousands of subscribers. Businesses relied on constant communication. Long-distance routes linked distant regions of the country. Inside the telephone exchanges, however, the system still depended heavily on human labor. Every call required an operator. Rows of workers sat at large switchboards, plugging cords into sockets and connecting lines one conversation at a time. In major cities, hundreds of operators handled the growing flow of calls. The work demanded speed, concentration, and endless repetition. As the number of subscribers increased, the limits of the manual system became obvious. Telephone traffic rose rapidly. More homes installed telephones. Offices placed instruments on desks throughout entire buildings. Banks, factories, hospitals, and government offices relied on the network throughout the day. Each new subscriber added more calls. Switchboard rooms grew larger, but the demand continued rising faster than the workforce could expand. During busy hours, customers sometimes waited before an operator could answer. Engineers began searching for a mechanical solution. The idea of an automatic telephone exchange appeared in the 1890s. An inventor named Almon Strowger developed one of the first practical systems. Strowger worked as an undertaker in Kansas City. According to a widely repeated story, he suspected that local operators were directing calls to a competing funeral business. Whether the story was entirely accurate remains uncertain. But Strauger's solution was clear: remove the operator. He designed a switching mechanism that allowed a telephone user to select a destination directly by sending electrical signals into the network. Instead of speaking with an operator, the caller would control the switching equipment through the telephone itself. The invention became known as the step-by-step switching system. Inside the exchange stood racks of electromechanical equipment. Vertical shafts carried rotating metal arms connected to electrical contacts. Each shaft could move upward and then rotate across different circuits. Every motion represented part of a telephone number. When a caller dialed a number, the telephone instrument produced a sequence of electrical pulses. These pulses traveled along the subscriber line into the exchange equipment. Each group of pulses moved the switch mechanism to a new position. Step upward, rotate, connect to the next circuit. The sequence repeated until the system reached the destination line. The switches then created a complete electrical path between the two telephones. For the first time, a machine could connect calls without human assistance. Early automatic exchanges remained relatively small. The equipment was complex and required careful maintenance. Many telephone companies continued relying on manual operators for years. But the advantages were obvious. Automatic switching operated continuously without fatigue. The equipment responded instantly when a subscriber dialed a number. Large volumes of calls could move through the system simultaneously. As urban populations expanded, the Bell system gradually introduced automatic switching into selected exchanges. These installations became increasingly sophisticated. Massive frames filled with relays and switches occupied entire rooms inside central offices. Thousands of moving parts worked together to guide calls through the network. Engineers designed the mechanisms with extraordinary precision, so each electrical pulse produced the correct mechanical motion. The sound inside these exchanges became distinctive. When calls passed through the equipment, the switches moved rapidly with a pattern of clicking and whirring sounds. Metal contacts opened and closed. Electromagnets pulled small arms into new positions. The room filled with a mechanical rhythm created by thousands of circuits operating at once. Despite the complexity, the equipment proved reliable. Telephone engineers developed strict maintenance routines to keep the switches clean and properly aligned. Technicians inspected the machinery regularly and replaced worn components before failures occurred. Automation also changed the way customers use telephones. Instead of speaking with an operator for every local call, subscribers dialed numbers directly. Rotary dials on the telephone instrument converted finger movements into electrical pulses. Each digit produced a precise sequence of signals. The switching equipment interpreted the pulses and built the connection. For the caller, the process felt almost immediate. Lift the receiver, dial the number, wait a moment while the switches moved. Then, the distant telephone began to ring. This new method transformed the speed of local communication. Calls no longer required an operator to answer and manually plug cords into a switchboard. The machines handled the routing automatically. Operators still played an important role in long-distance service. Complex calls between cities often required coordination between several switching offices and trunk circuits. But inside major cities, automatic switching gradually replaced many manual boards. The scale of the equipment reflected the growing demand. Central offices serving tens of thousands of subscribers required enormous switching installations. Entire floors of buildings filled with electromechanical frames. Bundles of wires ran between the racks carrying signals from one switch to another. Each completed call followed a temporary electrical path through this mechanical maze. When the conversation ended, the switches returned to their starting positions. The circuits cleared automatically and became available for the next call. Engineers continued refining switching technology throughout the 20th century. New designs improved speed, reliability, and capacity. The goal remained simple: handle millions of calls every day. By mid-century, large American cities operated telephone exchanges capable of processing extraordinary volumes of traffic. Electromechanical switching equipment worked continuously, connecting conversations across neighborhoods, states, and long-distance routes. Behind the familiar ringing of a telephone stood one of the most intricate mechanical systems ever built. Thousands of switches, miles of wiring, relays moving constantly as voices traveled through the network. The telephone system had evolved from a simple pair of wires into a vast automated machine capable of connecting millions of people. And the number of voices entering the system continued growing. Every new subscriber added more traffic. Every new city increased the scale of the network. The machines that switched millions of calls had solved one problem. They had made the telephone network powerful enough to support an entire nation speaking at once. Chapter 9: The Network That Ran the Economy. By the middle of the 20th century, the telephone had become a familiar object across the United States. Instruments sat on office desks, hung on kitchen walls, and appeared in hotel rooms, factories, and train stations. Behind that small device stood a vast national infrastructure. Copper wires stretched across cities, farmland, mountains, and deserts. Central offices processed millions of connections each day. Long-distance trunk routes linked the country from coast to coast. The Bell network had become one of the largest communication systems ever built. Its influence reached far beyond conversation. It helped run the American economy. During the 19th century, business communication moved slowly. Letters traveled by rail. Telegraph messages carried short instructions, but detailed discussions required face-to-face meetings. Negotiations often stretched across days or weeks. The telephone changed that rhythm. A merchant in Chicago could speak directly with a supplier in New York. A factory manager could contact distributors across several states in a single morning. Questions that once required written correspondence now received answers within minutes. The speed of business increased dramatically. Financial markets quickly recognized the advantage. Banks and brokerage houses relied on constant communication with partners in other cities. Telephone circuits carried market information between financial centers. Traders spoke directly with colleagues while prices were still changing. Investment decisions that once depended on delayed telegrams could now happen immediately. Banks also depended on rapid communication. A banker evaluating a loan might contact another institution hundreds of miles away to verify a customer's reputation. Credit arrangements required confirmation between multiple offices. The ability to exchange information instantly reduced uncertainty in financial transactions. News organizations found similar benefits. Editors needed constant contact with reporters working in distant locations. Telegraph messages remained useful for short updates, but longer explanations required conversation. Telephone circuits allowed journalists to describe events as they happened. Political speeches, courtroom decisions, and major accidents could be reported to newsrooms within minutes. Transportation industries also relied on the expanding network. Railroads had long depended on telegraph systems to coordinate train movements. As telephone lines spread along railway corridors, dispatchers gained the ability to speak directly with stations, maintenance crews, and company offices. Air transportation adopted the technology quickly. As commercial aviation developed during the early 20th century, telephone circuits connected airports with weather services, airline offices, and government regulators. Pilots and ground crews depended on rapid communication to coordinate schedules and respond to changing conditions. Retail businesses also adapted to the new speed. Department stores used telephones to coordinate inventory between warehouses and sales floors. Managers called suppliers when products ran low. Delivery services relied on calls to track shipments and adjust routes. A request from a customer could move through several departments within minutes. Factories used the system in similar ways. Industrial managers coordinated production between multiple plants. Raw materials could be ordered quickly when supplies began running low. Engineers consulted with specialists in distant facilities to solve technical problems. Production decisions that once required lengthy correspondence could now happen through a brief conversation. Government agencies also integrated the telephone into daily operations. Federal offices in Washington communicated with regional branches across the country through long-distance circuits. Military installations relied on telephone connections to coordinate logistics and training activities. Emergency services began adopting the system as well. Police stations installed dedicated lines connecting patrol units with headquarters. Fire departments used telephone alarms to mobilize crews quickly when reports arrived. Hospitals relied on calls to summon doctors and organize emergency treatment. Beyond business and government, the telephone reshaped everyday social life. Families used it to remain connected across growing cities and suburbs. Parents could check on children after school. Relatives shared news without waiting for letters. Invitations, arrangements, and personal conversations moved easily through the network. Telephone directories grew thicker each year. Large cities produced books listing thousands of subscribers. Operators handled enormous volumes of connections. Switching equipment routed conversations across neighborhoods and across the continent. The network operated continuously. Day and night, voices traveled through copper wires linking homes, offices, and institutions across the country. Maintaining that system required constant expansion. Bell engineers added switching equipment inside central offices to handle rising traffic. New trunk routes connected growing metropolitan areas. Transmission improvements increased the number of conversations that could move across the network simultaneously. Every improvement allowed more information to move faster. The effect on the economy was profound. Businesses began operating at a faster pace because decisions could be made quickly. Markets responded more rapidly to changing conditions. Information traveled between cities separated by thousands of miles in only seconds. The telephone did not replace transportation or physical trade. Railroads still carried goods, ships still crossed oceans, trucks still delivered products to stores. But the decisions guiding those movements increasingly traveled through telephone lines. A call placed in one city could influence events across the country. Orders issued through the network triggered shipments, contracts, and financial transactions. The system had become a kind of nervous system for the national economy. Millions of conversations passed through Bell exchanges every day. Some were personal. Others carried instructions and agreements that shaped the movement of money and materials across the nation. By the middle of the 20th century, modern business had become difficult to imagine without the telephone. Factories relied on it. Banks relied on it. News organizations relied on it. Government agencies relied on it. The network had become more than a communication tool. It had become an essential part of how the United States functioned. Chapter 10: The Breakup That Ended the Empire. For most of the 20th century, the Bell system stood at the center of American communication. Millions of conversations moved through its wires every day. Long-distance circuits linked cities across the continent. Telephone service reached homes, offices, factories, and government buildings. The system appeared stable. One organization controlled most of the infrastructure. Federal and state regulators supervised prices and service standards. Customers leased their telephones from the company and depended on the same national network. For decades, the arrangement seemed permanent. But during the 1970s, pressure against the Bell monopoly began growing. The telecommunications industry was changing. New transmission technologies allowed signals to travel through microwave relay towers instead of only through copper wires. Computer systems began sending digital data through telephone circuits. Businesses and technology firms started asking a new question: why should a single company control the entire network? Several competitors wanted access to long-distance routes. Others wanted permission to attach new electronic devices to telephone lines. Computer companies believed existing circuits could carry digital information as well as voice. The Bell system resisted many of these proposals. Executives argued that the network worked best as a unified infrastructure. Fragmenting the system, they warned, could create technical instability and reduce reliability. Regulators and competitors disagreed. They believed the company's control over local service allowed it to dominate the entire telecommunications industry. The conflict moved into federal court. In 1974, the United States Department of Justice filed a major antitrust lawsuit against American Telephone and Telegraph. The government argued that AT&T used its control of local telephone service to block competition in long-distance communication and equipment manufacturing. The case threatened the structure of the entire Bell system. For years, the lawsuit moved slowly through the courts. Economists, engineers, and executives testified about how the network operated. Judges examined switching technology, transmission systems, and the organization of the national telephone infrastructure. The central question remained clear. Could one corporation control the primary communication network of the United States? By the early 1980s, negotiations began moving toward a settlement. The agreement reshaped the industry. In 1982, AT&T accepted a plan that required the company to give up control of its local telephone operating companies. These regional providers would become separate businesses responsible for local service. On January 1, 1984, the plan took effect. The Bell monopoly ended. AT&T retained its long-distance network, research laboratories, and manufacturing operations, but the local operating companies were reorganized into 7 independent regional carriers. The public soon gave them a nickname: the Baby Bells. Each regional company controlled local telephone infrastructure across a different part of the country. They inherited switching offices, maintenance crews, equipment facilities, and millions of customers. For many Americans, daily telephone service continued without visible change. Local calls still worked. Telephones still rang. Conversations still traveled through the same copper lines installed decades earlier. But the structure behind the system had changed. Competition slowly entered the telecommunications industry. New companies began offering long-distance services. Alternative equipment manufacturers entered the market. Computer networks expanded their use of telephone circuits to move digital data. Meanwhile, technological change accelerated. Inside Bell Telephone Laboratories, researchers had spent decades studying electronic communication. Their work produced some of the most important inventions in modern technology. In 1947, Bell scientists developed the transistor. This small electronic device replaced bulky vacuum tubes and became the foundation of modern computers. Bell researchers also pioneered digital switching, satellite communication systems, and new methods for transmitting information across complex networks. Fiber optic technology soon replaced many copper transmission lines. Instead of electrical signals moving through metal wires, pulses of light traveled through strands of glass. A single fiber could carry enormous volumes of information across continents and oceans. Telephone networks gradually evolved into digital communication networks. Computer systems began connecting through telephone circuits using modems. Universities and research laboratories built experimental data networks linking computers across long distances. From these early experiments emerged a new form of communication: the Internet. Ironically, many of the technical foundations behind this transformation came from research conducted within the Bell system itself. Decades of work on switching networks, signal processing, and electronic components helped create the architecture used by modern digital networks. The monopoly that once controlled American telephones had helped build the tools that would transform global communication. Today, the telecommunications landscape looks very different. Wireless signals travel through the air. Fiber optic cables carry data across oceans. Smartphones connect billions of people across continents. Yet the roots of these systems trace back to the infrastructure created during the Bell era. Engineers who designed long-distance circuits, switching networks, and transmission theory established principles that still guide modern communication technology. The Bell system began as an experiment in sending a human voice through a wire. Over the next century, it built one of the largest technical networks ever constructed. Miles of copper lines, thousands of switching offices, millions of telephones linking homes and businesses across a continent. The empire that controlled that system eventually disappeared, but the infrastructure it created changed how societies communicate. From the first fragile telephone circuits to today's global internet, the story follows the same idea: connecting people across distance. The Bell system wired a nation, and in doing so, it helped build the communication era that followed. The Bell system is gone, but the world it created never disappeared. Its wires may have faded, its switchboards may have gone silent, and its monopoly may have been broken apart, but the logic behind it still surrounds us. The Bell system proved that communication could become infrastructure, something so essential that daily life, business, government, and culture would all depend on it. What began as Alexander Graham Bell's fragile experiment became a machine that carried the voices of a nation. It stretched across mountains, farms, and cities. It connected families, drove markets, coordinated railroads, powered emergencies, and helped build the pace of modern American life. And when it finally broke apart, it didn't end the communication age, it opened the door to the next one. Because the internet didn't appear out of nowhere. It arrived on foundations Bell helped build: switching, signal theory, long-distance networking, electronic research, and the idea that technology could collapse distance itself. So when we look back at the Bell system, we're not just looking at old telephones and tangled wires. We're looking at the moment America first became truly connected, and the blueprint for the digital world that followed.